So let's look at primary distribution. Primary distribution is a link between transmission and distribution systems. So remember we mentioned that Nairobi has a ring of 66 kV going all around it. Now, because Nairobi is a large load center, those receiving stations receive power in bulk, in huge quantities. And it would not make sense, even if your house is right next to Juja substation, you would not get your power directly from Juja receiving station. It has to go through a series of lower and lower voltages, substations which bring it down to a more manageable level. And that is the purpose of the primary distribution network. You have your transmission, or which is at, in the case of this example, it is at 33, but it can also be at 66 kV, whereby your power now comes in the form of 11 kV, and it will go to some substations. So now these 11 kV lines form a lower level of voltage which distributes around a localized area. And then these substations in turn, which are here, now come and form your secondary distribution. So this represents what is coming from your substation. So your substation here, we said will have a number of feeders, and each of these lines, if I can draw an intermediate diagram here. So this is your substation, and you would have a feeder at 11 kV. Now along this line of 11 kV, you would have a series of transformers like that, which step down to 415. And then these now distribute to your various consumers. So this line here, this section here of a single transformer with its line is what we would indicate below. So it's a series of ever reducing supplies, and so on and so forth. Okay. So at each level, you have various step downs. So now at the point of the secondary distribution, where you have now this transformer, which we have seen here, one of the transformers that comes off of a feeder. Okay. This can be a pole mounted, it can be ground mounted, it can be, there are various other options that you have. It can be of various sizes. You can have a transformer that has, 315 kVA. You can have transformers of 1 MVA, and so on and so forth. So these ones will generally receive at 11 kV and distribute at 415. What we would want to see from this diagram is how you get from 3-phase to single phase. You have 400, okay, in this particular case it's 400 to 230, but in the Kenyan case it would be 415 to 240. So this case, we have small consumers, right? So you have every consumer. So if this is house number 1, you have your house with your family. You don't need huge amounts of power. You only need, say, around 100 amps of power at any given time. That means you only need single phase. So for a single phase, you would tap from the neutral and you would tap from one of the phases. Same with your neighbor, he would tap from the neutral, but you can also tap from a different phase. And your other neighbor would tap from maybe the red phase up here. When the power distribution company, Kenya Power, is connecting, say, an estate with various houses, they will try to do load balancing so that everybody is connected in such a way that the ultimate load is evenly distributed among the 3 phases that you have there. In some cases, you would also have, of course, your factory or your large building or your institution, which takes directly at 3-phase and is metered at 3-phase. The power meters are at 3-phase. Okay, so that person would still be connected to this low voltage circuit, but they would pick their power at 3-phase. So one thing that you'll notice here, at the distribution level, at the lowest voltage that you have, secondary distribution, this is a 4-wire system. The reason for that is you have the neutral. The neutral line is introduced at the transformer in the distribution system. So these pole-mounted transformers, the incoming lines are 3-wire, okay? But the outgoing for a low voltage transformer, out will always be 4 wires. The reason for that is it is connected in a star configuration, and you have a neutral all along from the generator all the way through transmission, all the way through primary transmission. You will have 3-wire systems there is no neutral introduced until the point where it needs to be consumed. And the neutral is introduced by the configuration of your transformer. So now let's look at a number of questions that we had asked. So number one is, why do we transmit at high voltage? Let's say, for the purposes of understanding this, let's say we have a load of 10 megawatts. Your 10 megawatts comes from your generator through a power line and goes where it is consumed by your consumer. Now, if your consumer is any distance away from you, your transmission line can be a number of kilometers long, and it consists of, as we have said, practically 3 wires. So this line, because it is many kilometers long and it is made of a metal, either copper or aluminum, that metal has a resistance in it. And anytime you have a resistance and there's a current flowing, you will have losses. And those losses are dictated by this formula: the square of the current that flows through it times the resistance. Now, your wire itself, the resistance of your wire is dependent on those 3 things. This is your resistivity, this is your length, and this is your cross-sectional area. That determines the resistance, how much power you will lose in taking your power from your generating station many kilometers away to your consumer. The resistance of the wire itself will not change. The resistivity is a characteristic of the metal itself. That does not change. The length of the wire is fixed. You must, if it is 10 kilometers long, it must be 10 kilometers long. You won't change that. Same with the cross-sectional area. Once you have put up that wire, you can't go and change its characteristics. So that is fixed in this particular case of ours. So what you can do to minimize your losses is to change the current. So how do we go about that? Now, when you have power being transported or power being transmitted, value of the power is given by 3 times the voltage times the current. 3 because it is 3 phases. So the amount of power, if you have your 10 megawatts flowing through your lines, the amount of power that you can carry depends on your voltage and your current. Now, going back to our losses, you want to reduce the amount of current that that is passing through your conductor. So how do you go about that? If you want to reduce this, what happens to the voltage? The voltage has to be increased. You would transmit the same power with a low voltage and a high current, or a high voltage and a low current. So let's take, for example, if we were to transmit it at 415 volts. Let's rearrange it. So this, if we rearrange it, current is equal to power over 3 times voltage. So now at 415, what is the current that you are carrying? The power is 10 megawatts times 10 to the power 6 divided by 3 times 415. So 10 megawatts divided by 3 times 415 gives you, this is 803 amps, right? Now, if we were to transmit at 220 volts, what would now happen to us? Your current is that same, so 1 times 10 to the power 6 over 3 times 220 times 10 to the power 3. So it's 1 times 10 to the power 6 divided by 3 times 220 10 to the power 3. This current you will now have is 1.5 amps. So straight away what you can see, if you have at 220 kV, a very high voltage, the amount of current that you will carry is very, very low compared to if it was at 415 and you have a high current. So that reduces the amount of losses. You can imagine the losses that you would incur, 800 squared times whatever resistance it is, you would lose quite a large portion of your 10 megawatts that you want to supply. But if you take it to 220 kV, you can have it crossing the large distance that we are talking about at 1.5 amps. you have very low losses, and most of what you are putting in at the generator side, you will receive it at the load side. And that is why then you will now have your generator connected to transformers, and then your transmission line, and then your loads. But AC does have certain limitations. So some of the limitations include the cost of conductors and insulation. One might argue that if you are carrying it the way you would carry water or fuel, it may require less expensive infrastructure. So the infrastructure itself, and this is a limitation not just of AC, but any form of electricity, the infrastructure is costly. Cost of transmission structures and substation. Now, the advantages of AC are a bit clearer. I'll just list them. So we have number one, reduced volume, and number two, you have increased efficiency. So these are the advantages of AC over DC.